So I'm Nate Novak. I'm from Orca Maritime, like you said, down in Imperial Beach, California. Thank you for joining me as I'll be discussing mapping underwater explosive remnants of war using AUV mounted sensors, ROV videos, and ArcGIS in a complex seabed environment. So I'll just be telling you a little bit about how we collect, process, and share survey data from our underwater unmanned systems. Orca Maritime specializes in underwater imagery and data collection. So here are some of the sectors that we serve. We typically use autonomous underwater vehicles, remotely operated vehicles, towed systems, and divers. And as you can see, we integrate both commercial and government capabilities into long-term solutions for a wide range of clients. Here's just a small example of a night operation deploying an AUV in the Bay of San Diego. A lot of times we operate in the evening to avoid daytime maritime traffic in the channel. So if you're not familiar with an AUV, it stands for Autonomous Underwater Vehicle. It's a tubular vehicle that runs completely separate from any tethers or anything like that. And here's a short video what it looks like as it swims through the water column. So we build underwater geographic information systems and customized components to complement these existing GIS programs that the government has, as well as standalone planning tools. So many of our products contain detailed geodatabases, and they typically comprise of bottom objects and any pertinent environmental data, any contacts, areas of interest. So with this data, we usually create a fully navigable web-based web map, web app, any type of web scene that the client requests. All the elements of these comprehensive underwater surveys are typically compiled to deliver an accurate, layered geographic information system. So these are some of the data types that we hold in our geodatabases. These products are important because they serve as decision tools for project managers, which include, information-rich and GIS-centric formats to support emergency action plans for military and commercial port security organizations, engineering maintenance plans, and environmental protection initiatives. Throughout the world, explosive remnants of war, otherwise known as unexploded ordnance, or UXO, are continuing to become an international problem. So as communities, nations, and industries are moving into the maritime environment, they're becoming a large threat to operations in construction, energy, mining, fishing, tourism industries. So these explosive remnants of war are typically from historic amphibious battles, ordnance dump sites, sunken ships, and other war-related operations. In this video, our Ocean Server Ivor 3 AUV is towing a Marine Magnetics Explorer. So the Explorer magnetometer is an instrument that measures direction, strength, or relative change of a magnetic field at a particular location. I'd like to walk you through a brief overview and how we collect AUV data from a recent survey involving both sonar and magnetic sensors. When we're collecting the data, we try to be as time efficient as we can. So we use as many mission planning tools as possible. Vector Map is an Ocean Server proprietary software that allows us to plan our missions. As you can see, you can set all the vehicle parameters from this program before you deploy the vehicle. We typically have it ready to go the day before our mission. Another thing to mention is in hazardous locations, a GIS that's populated can be incredibly helpful for situational awareness of the surrounding environment. On the left is an example of how the AUV collects side-scan sonar imagery from dual sonar transducers. As it performs its mission, the sonar transducers collect collect data from the water column and the seabed. And dual side-scan sonar transducers also collect co-registered bathymetry using fundamental acoustic remote sensing to capture all the data. So what I want to do now is just walk you through a little bit of how we process the side-scan sonar data, as well as the bathymetry and all the magnetometry data. So the data processing workflow is quite simple. We collect the data, we process all of the data, we integrate it into the ArcGIS platform, and we develop ways to share our data with our clients using systems of engagement. We collect and post-process bathymetry in a survey like this, not as a focal point of the survey, but just to give us a sense of what the survey area looked like. In this survey, we ran the side-scan sonar, and we just collected bathy as we went. The red areas indicate shallow areas, and the blue is the deep water. We use Chesapeake Technology SonarWiz. It's a specialized sonar post-processing software that can be used to process side scan as well as manage all of our contacts. So we were able to locate munition rounds as well as measure dimensions based on width, length, and shadow. And during our post-mission analysis, the side scan sonar showed that these likely were artillery rounds from World War II on the portion that consisted of a flat, smooth bottom. So we used high-frequency sonar, 1600 kilohertz from the Ivor 3 mounted EdgeTech 2205, and we were able to detect and identify the UXO presence in areas with a low level of clutter, also known as a non-complex bottom. On the upper right-hand side, you can see the blown-up version of the munition rounds. So when we ran the side scan mission, we noticed the small contacts right here. So at that point, we knew that we had found a UXO field in an area that will for now be unnamed. So using side scan alone can prohibit the ID of munitions due to bottoms like this. So this is a cluttered bottom. It's unlikely that you'll find a 12-inch round clutter in a cluttered environment amongst rocks, and all the objects create a very difficult post-mission analysis session. So we went to the next logical thing, which is using the mag. So this is all the raw data collected from the vehicle. So we ran an AUV with a magnetometer running 6.4 meters behind the AUV in order to avoid any magnetic disruption. So the box at the bottom shows the magnetic calibration, and then you can see the tie leg running across the survey to measure total magnetic field. The mission ran for 4.5 hours, collected 50,000 data points, and had a 5-meter track spacing. So ArcGIS was used to clean up the raw data file in order to retain only valid magnetometer samples and remove any erroneous data. The side scan sonar mosaic was imported into ArcGIS in order to overlay both data sets to see any patterns. So side scan sonar mosaic initially showed some areas of scattered what we thought were abandoned munitions. However, we did not know the extent of how many munitions were in the area. Geoprocessing tools were used to create magnetic flux lines and to represent the magnetic field in the survey area. So you can see the densely placed lines show the presence of magnetically induced disruptions in the field. So ArcGIS allowed us to create the flux lines, and you can see a continuation of the magnetic disruption, not only in the simple non-complex bottom, but also continuing up to the complex bottom where we hadn't found any munitions amongst the rocks. So if the discarded munitions follow this pattern through the cluttered bottom, it could confirm a dump path of a World War II ship. So I'm going to quickly show you a video of the footage of the ROV traveling east along the UXO field. So this is the non-complex bottom. As you saw from the side scan sonar imagery, it was very easy to identify this amongst the non-cluttered bottom. Because we were unable to visually pinpoint UXO within the cluttered rocky area, we also deployed the ROV in the northern section to attempt to locate the UXO indicated by the magnetometer data, where the ROV icon is. Okay, so this is what the munition looks like amongst the rocky bottom, and therefore we have found munitions in a UXO field, and we will continue to run another few missions to kind of see the entire dump path of the area. Thank you.
All right.